Okay, as I resume recording. Okay, welcome back today. It's going to be, again, a short finish off of the lecture that I was giving yesterday. This was the last slide that I talked about effect size. And basically, it's how big an effect is. As clinicians, people working in medical research, this is obviously important. Is a treatment effective or not? It may be statistically significant, but actually really be of no use in practice. So this is important. I mentioned Cohen's d, which is a standardized effect size, which is how large the effect is, the difference in means divided by the standard deviation, not the standard error. Why not the standard error? Because we don't want to take sample size into account, okay? So in fact, Cohen's d is just like Z. It's the same formula, actually. Okay, I mentioned odds ratio, which I think you've done. So what's the null hypothesis for an odds ratio? Right. Okay, what's the null hypothesis for a treatment effect?
It's the effect isn't significant?
No. You mean statistically significant?
Yeah.
No. So it's going to be a mean value. What would be, if we had positive values being that it's effective and negative values that it actually makes patients worse, what would the null hypothesis be? Negative? No. Okay, we're covering all the bases here. Someone's going to get it right. Just what? Is it effective? Well, the null hypothesis is not that it is effective. No. The null hypothesis, null means nothing, no effect. What was our null hypothesis in the example that we did before? It was that the anxious patients had the same blood pressure as everyone else, right? So 105. So if a treatment is having no effect at all, that would be the null hypothesis. In other words, 0. Okay, so null hypothesis is 0 if you're looking at that. For the odds ratio, this is a ratio. Can you get an odds ratio of 0? No. Okay, so what would be the null hypothesis for an odds ratio? Have you forgotten this? You did this some weeks ago, right? Okay. Okay, it's when the odds are equal, okay? So that'll be what's on top is the same as below, so that'll give you 1, right? That's the null hypothesis. So if the treatment is effective, then the odds ratio will be greater than 1. And if it is making patients worse, then it'll be less than 1, okay? That's how generally they work out the odds ratio. So if you read a clinical paper and it shows that the odds ratio is 1.5, then you know that the treatment is having some positive effect. Whereas if it's 0.5, then you would know that it's not, it's actually making patients worse. Okay, I talked about effect size. You can collect data, or you can estimate, you can suggest a value that is of minimum clinical importance. This is pre-study, or you can actually collect the data and that'll tell you about how large the effect is. Okay, and there's this good paper here that I want you to look at. I've got it here. So using effect size and why the p-value is not enough. So Jacob Cohen, I mentioned Cohen's D. This is what he said. The primary product of a research inquiry is one or more measures of effect size, not p-values. So he's de-emphasizing p-values. Okay, so I recommend that you read this. Okay, so on to today's lecture. So what we have here is a table that has got the effect size along the top and the p-value on the vertical axis, if you like. So if we've got a small p-value less than 0.05, then that's would be statistically significant, all right? If it's larger than 0.05, down here, large p-value, that would not be statistically significant, and we would not say that there was an effect there. We would say there's not enough evidence for an effect. Okay, so effect size, as you now understand, a large effect size is good, small effect size is not very interesting. Okay, so let's start with the green squares here. Let's say we've got a small p-value, so let's say it's 0.01, which means that it would be statistically significant, right? And let's say we have a large effect size. Now this is good, that's why I say no problem here. That's good because the treatment is benefiting, it's having a large effect, okay? A large beneficial effect, and it is statistically significant. So you can convince people that not only is the treatment really doing something, but it statistically is credible, and it's unlikely that the results are simply due to chance or sampling variability. They could be, but it's unlikely. What about the other green square here? This is where we have a large p-value, all right? So let's say the p-value is 0.3, that's much larger than 0.05. We would say, okay, statistically, this is not significant. But this is for when there's a small effect size. So actually, there may be some difference. So there may be some effect of the treatment, but it is rather small. So we've got a small effect that is not interesting anyway, and also a large p-value, which tells us that statistically it's not significant. So this also is not a problem, but the two other squares, there are problems. So let's start with this one here, where we've got a large p-value again. Okay, it's 0.3, but we see that the treatment seems on average to have a big effect, okay? But maybe we've only got a few patients, only got 3 or 4 patients. So there's a big effect there, but because of the small sample size, we don't achieve statistical significance. So this is a problem. The other problem is the other way completely, and that is when we've got a small p-value. So our p-value, let us say, is 0.001. It's a very small p-value, but the effect size is also very small. So there are some studies that, for example, use 1 million people. They will be able to detect very small effects. And I showed you with a confidence interval yesterday, the larger your sample size, the smaller the confidence interval, and the smaller the effect that you can detect statistically. So this again is a bit of a problem. So big data is not good, actually, it turns out statistically. What we want is actually smallish data, not very small, but small enough to get statistical significance and that reveals an effect size that is of clinical importance. Yes, asking a question.
So in both cases, would you just change the sample and redo you would recalculate the p-value?
The red, where the red ones are. Okay, for this one where you've got a small p-value, it's statistically significant, right? But a small effect. There's no need to redo. You've got a lot of data and it's telling you that the treatment is basically doing next to nothing. It's having a trivial effect. Okay, so it's decreasing the blood pressure. Let's say a hypotensive drug. It's decreasing blood pressure by 1 millimeter of mercury. No one's actually interested in a drug that has such a small effect. But you will see in the literature papers reporting this sort of result. So it's important that you understand this. This one, the other one where we've got a large p-value and a large effect, sure, we've got to collect more data, do another study, basically. Yeah. Thanks for the questions, good. All right. So any other questions? No, okay. All right, so on the basis of a p-value, we make a decision whether or not to reject the null hypothesis. Okay, so this is the 0.05, 5% level. If we get a p-value that is less than that, we say, yes, there is a statistically significant effect, and we reject the null hypothesis. However, that decision that we make is subject to error, particularly type 2 error. Okay, I haven't talked about type 1 and type 2 error. Type 1 error is when you reject the null hypothesis when the null hypothesis is actually true, okay? And type 2 error is the kind of opposite of that. It's where you do not reject the null hypothesis, but the null hypothesis is false, okay? So type 2 error, and this is where the absence of evidence is actually not evidence of absence. So it's like in the previous slide here, where you don't get a small p-value, okay, you get a large p-value, but there is an effect there. It's quite a large effect, but it just doesn't come out statistically significant. You can't just conclude from that that there's nothing happening, that this drug doesn't do anything, okay? It may be when you collect more data, it turns out it doesn't do anything, but actually on the face of it, you could be making a type 2 error here. Really, you need more data. Someone asking a question? Yes.
A type 1 error, the probability of making a type 1 error would be alpha?
Yes, exactly. Exactly. Well done. Good. Okay, we will get onto this in a future lecture. Yeah. Okay, the use of confidence intervals helps to determine whether this type of error has been made. So it also helps decide whether the magnitude of the effect that we have observed is of scientific or clinical interest. Okay, so this slide, I'm going to work through this. What we have is the null value here, this line at 0, and then the effect is shown on this vertical scale here. And the red dashed line, this is an important effect. So round about 4 point something, 4.5 or something, it looks like this means that there's a clinically important effect, okay? So I'm just going to work through the means here. So scenario A here, we've got a mean here at 7, and the confidence interval is shown by the line. So this is the lower limit, here's the upper limit, okay? So this confidence interval, does it include the null value? No, it doesn't. The null value is right down here. So it's very well clear of the null value. So we would immediately be able to say, okay, it's statistically significant, all right? What about, does it include the importance value of 4.5 or whatever? Also no. So it's significantly better than our clinical marginal value that is of importance. Okay, so we can say this is a good result. If we got a result like this, then we'd be very happy because statistically it is significant against both the null hypothesis and the minimal value that is of clinical importance. Okay, what about B? This is a bit more dodgy. I'm working downwards, getting more and more dodgy. So B is here. We have a result at 5, roughly. And the confidence interval here, does that include the null value? No, it's null is right down here, so it's clear of that. So we would say this is statistically significant. However, it does include some values that are below this line of importance. Okay, so it suggests it could be important. Okay, let's get down to this case here. This one, does this confidence interval, this is at about 2, the confidence interval, does this include the null value? No, again, it's pretty close to it, but it doesn't include it. So again, we would be getting a p-value less than 0.05. We would be saying, okay, yes, great, there's a statistically significant effect. However, like I was saying, if it's only 1 millimeter mercury decrease, this is the same result. It may be statistically significant, but it's not clinically important because the confidence interval doesn't include this value up here, the dashed red line where the limit of, or the minimal clinical importance is found. Okay, so this result here is actually statistically significant, but not clinically important. So I've got here, these are the three results, and if you read these, the red indicates definitely important, not important, but this one, this is possibly important. Maybe if we did another study, improved our study procedure, maybe or used a higher dose of the drug or something, it might show a stronger effect. Okay, now let's move on to scenarios D and E. So look at D. We've got a result. Yes?
I can ask a question.
Okay.
For the confidence interval, should it include the null hypothesis only, always within, so the null hypothesis will be inside the 95%?
No, it always includes the sample mean. Okay. It sometimes includes, see the sample mean in each of these is in the middle of the confidence interval. So these circles, this is where the sample mean is, all right? The null hypothesis value here, in this case it's 0, it's down here, and it's not in these three scenarios, but it is in these D and E scenarios, okay?
So because significant it is less than 5%, so the 95% will be null hypothesis, right?
Yes, that's right. I'm talking about 95% confidence intervals, yes. But the confidence, 95% confidence intervals are symmetrical, in this case, around the sample mean.
Okay, thank you.
Okay, so let's look at scenario D. Now, if we ask, does this include the null value? Yes, it does. It crosses this 0 line. But it's interesting, it actually crosses the important line too. Now this mean is actually the same as the previous scenario C here. So this is not statistically significant because the null value is within the interval. However, it does include the minimal clinical importance value. So really what we can say about this is it's inconclusive. Really we need to repeat the study with a larger sample probably, okay? Okay, let's look at E. So here, what about this case? So what we've got here is it statistically significant? It's not significant because it includes the null value. The null value is actually very close to the sample mean. Does this interval include the minimal importance line? No, that's up here. So what we can say for this is that there is, it's not statistically significant and there's anyway no indication that it has any clinically important effect, okay? There may be a tiny effect here, but it's nowhere near what we need for clinical importance. Okay, so this situation here is like one of the scenarios in the previous slide where we had a large p-value and a small effect size. Okay, any other questions?
There's a question about the table of slides back. So she's asking where the first box on the last box. Does this mean the probability of having an effect is small, but we actually got a large effect?
Which one? This one? Talking about this?
Yeah, she's referring to the first box.
Yeah, this box, yeah. This is when it's statistically significant and there is a large effect. So that's good. That's like scenario A in the slide we were just looking at. All right.
I think her description describes the one below it.
Oh, okay. Where we've got a large p-value. Okay, large p-value, so this is where we might have a p-value of 0.5. Okay, that's much greater than 0.05. And the effect size is large, so it's looking promising. However, it doesn't come out statistically significant. So this is a bit of a problem. And usually the problem is you don't have a large enough sample size. Okay, because the sampling distribution and the standard error depends upon, it's inversely related to the square root of the sample size. Okay, so as you increase the sample size, the standard error gets smaller, and then you can detect you can detect effects more easily. Okay, and the last scenario is scenario E. This is when we had a large p-value because it wasn't significant and a small effect size. So let's just go back down to here. So here, that's, yeah, E is this one where we've got a large p-value because it's not statistically significant. It includes the null value and the effect is very small. It's not anywhere near being clinically important. Any other questions? Okay. Right, so I'm just going to repeat this pretty much. I think repetition may help people understand. I don't know, sometimes it puts them to sleep. Let's try. So I've got the scales different here because we're talking about IQ here, all right? Everyone knows IQ 100, that's where the population mean is, this dashed line here down to 100. We're interested in a 10-unit increase. So let's say we're doing a study where we're giving vitamins to children, okay, for a year, and then we measure their IQ after a year of these vitamins. If it gets up to 110 or more, then that would suggest that the vitamins are helping their intelligence. If it's close to this 100, then it suggests the vitamins are not doing anything really. So let's look at the first scenario. The lines with the little arrows here, this is the 95% confidence interval. And in the middle, the black dot, that is the mean, the sample mean. So our sample mean is here. It's at about 104, something like that. Okay. Is this statistically significant? Yes, it is, because it doesn't include the null value of 100. Okay, is it significantly different from this 110, which is what we want to be of practical importance? It's not included, is it? So it's significantly different from this too. So what can we conclude about this? Okay, we can conclude that it is statistically significant, all right, because it doesn't include the null value. What about practical importance or clinical importance? It's not, that's right. It's significantly less than this value of 110. So we would say, yes, this is statistically significant, but not of practical importance. Okay, what about scenario B? Okay, so B, this is nice. We've got a very large mean up here, 128 or something. And the confidence interval is quite large, but it is well above both the minimal value that is of practical importance and the null hypothesis. So is this statistically significant? Yes. Is it of practical importance? Yes, it's above. Okay, so it doesn't include these values. This is an impressive result. Be nice if you got this sort of result, very clear. So we would say, yes, this is statistically significant, and these vitamins are really improving IQ. Every child should be given these vitamins. Okay.
I have a question, Doctor.
Okay.
The clinical importance dashed line.
Sorry?
The clinical importance
Yes.
dashed line.
Yes.
How would you get that? Is that something that's
that's
objective?
It's a good question. I mentioned heart, blood pressure yesterday, and it's got to be someone who is an expert in the field needs to decide this. If you don't know anything, then you can use something like Cohen's d, which is a standardized measure of effect size. So if you get, so standardized means that a d, Cohen's d of 0.2, you would say that's a small effect. 0.5, we would say a medium effect. And anything above 0.8, you would say is a large effect. So let's say you had a d of 1.5, then that would be a very large effect, okay? The example I gave you yesterday was, I think, actually it was talking about effect size, wasn't it? So students, university students, they have IQs of about 120 on average, okay? Compare that with the mean of 100, okay? So that's a 20-point difference. What's the standard deviation? It's about 10. So in fact, that's a huge D, it's 2, okay? 20 divided by the standard deviation of 10, that gives us a D of 2. So that's a big effect size. Does that answer your question? It's a specialist type of thing you have to decide. I'm just making it up here as a particular example. I think it's reasonable to say that, I don't know, boosting children's IQ by 10 units would be beneficial. If I was to say, well, I think it's only 1 unit, I think you'd just laugh and say, well, 100 versus 101, it's not going to make much difference. It's such a small, trivial effect that no one would be interested in taking vitamins to boost children's IQ by just 1 unit. 10 units, I think, is more credible. Okay, any other questions?
There's a question in relation to that. So Sadar, she's asking, is A practically unimportant because it is less than 1/10?
Yes, yes, because this is less than, in fact, it's significantly less than 10. So we can say statistically significant from the null value, true, but statistical significance is not everything. It's actually whether it is of practical importance or clinical importance. And this scenario A clearly is not of importance. And this result is conclusive. Okay, so you can publish this and people will say, oh yeah, it comes out statistically significant, but actually it's also significantly less than 110. So clearly it's not worth using these vitamins at all, okay? B is also very conclusive, this result. We've got a large effect and it is significant both with reference to the null value and with reference to the minimal difference of 10 units. Now, what's interesting here is that if you were to work out the Z values, all right, for these 2 studies, okay, they would be the same. Now, the Z value, this, if you remember, okay, 2.5% in each tail. Do you remember that number 1.96 from yesterday? Must be a number that kind of familiar with, yeah, 1.96. We looked it up in the Z table. All right, so that's almost 2, right? It's close to 2. So in order to get the 95% confidence interval, we had to multiply 1.96 by the standard error. So this point here is nearly 2 standard errors below the mean. And this point here is nearly 2, 1.96 standard errors above the mean. Same for this. This is 2 standard errors below. This is 2 standard errors above. Okay, so what we can do is Z represents the number of standard errors, right? So actually there's 2 from here to here, roughly, and then another 2, and then another 2. So actually the Z value here is 6, 2, 4, 6. And for this one, it's the same. There's 2 to here, 4, 6. All right, so our Z values will be the same. And the P values will be the same. Because when you look up a Z, you look up a Z value of 6, actually it's points, lots and lots of zeros, probably about 12 zeros, and then 1. Okay, let's go on to the next scenario. This is just explaining what I've explained. You can read it and check it out. And I say here 6 standard errors above and so on. So just what I've been explaining. Let's look at scenario C. Okay, so this is a slightly dodgy result, isn't it?
But there's a
Question? Okay.
They're asking how did you know the Z value or the Z value?
Because Z represents the number of standard errors that the mean is away from the null value that we're testing. Okay, so we're just doing it with respect to the null. We're not doing it with respect to this value of 110, although we could if we wanted to, but let's do it just with respect to this 100. So the number of standard errors from here, from the mean to the edge of the 95% confidence interval is nearly 2, plus another 2 to here, another 2 to here. That gives us 6 standard errors, which is Z equals to 6, if you look at the formula.
That's-
Okay.
Is it always fixed?
What's fixed?
Which means the Z.
No. It's the number of standard errors away from the null. That's what we're testing. So we're testing our sample mean, our observed data, versus the null value. How far away is it in terms of standard errors? That's what it is. This is a made-up example, so I've kind of made it nice for everyone so that these are actually both got the same Z values, but you know, if you were to repeat this study properly, you'll probably get a result here, not right up here, but you know, it depends. You're going to get different results every time. So this is just for explaining. Okay, so let's look at C. 100 is this dashed line here. Is this statistically significant? No, because it includes the null value. The mean is quite close to 100, so it doesn't look like the vitamins are doing much. And this doesn't include the value of 10, which is our minimum practical importance. So what we can conclude here is that it's not statistically significant or of practical importance. Okay, so this is conclusive. We can write up the paper a bit like both scenario A and B. We can publish all of this, although journals tend not to like publishing data where the p-value is greater than 0.05, which is what we've got here, a non-significant result. Okay, what about this case D? So what we've got here is a mean that is very close to 110 and a massive confidence interval like this. What can we conclude? Well, does it include 100, the null value? Yes, so it's not statistically significant. However, almost half of this confidence interval is above this mean of 10, the value of 10, 110. So this is really inconclusive, this result here. It would be difficult to publish this result. I think they would say, well, okay, it's not significant. It looks like promising, but it's not significant. Maybe you need to repeat the study with more data. Do you have a question? Okay. Okay. All right, so where do we go? So yeah, just for fun, I've made it so that the Z values here are the same again. Okay, so C and D have got the same Z value. Remember, from the mean to the end of the confidence interval is about 2. So here is about 1. Okay, so our Z value is 1 here. It's the same here. From this mean to the dashed line, it's about 1. Okay, Z is equal to 1. So our p-value is... What? Hello? Okay. So our Z value is going to be the same and our p-value is going to be the same. So what is the p-value roughly? Well, to remember that Z table, Z is equal to 1. We got 15.83% or something. So if you've got to do that 2 tails, so it's going to be about 32%, so 0.32, something like that. Yeah, about so the p-value will actually be the same, 0.32 in both of these scenarios. Now it's interesting that in C, we can come to a conclusive, we have a conclusive result, all right, and we can publish this. In D, we cannot, and yet the Z and the p-values are exactly the same, all right? So this is why the p-value is not always a good guide to what's going on. You need to use confidence intervals to see what's happening. Okay, so This is just explaining what I've already explained. So the Z is equal to 1 for both of these. And here are the 4 scenarios again. Okay, so all right, so I haven't talked about power yet, statistical power, and I will do that. If we've got a 95% confidence interval that includes both values consistent with the null hypothesis and those for an interesting effect according to the alternative hypothesis, then this suggests that the power of the study was too low. If the power of the study is too low, that usually means that you don't have enough patients, you don't have enough participants in your study. So let's say we regarded an effect in excess of 10 IQ units, just like the example that we had earlier, above 100 to be of practical importance. And we were looking at the effects of omega-3 fatty acid supplements. Let's say we got this result. This confidence interval spans both 100, which is the null value, and 110, which is our value of interest in terms of practical importance. So this is like scenario D in the previous slide. This tells us straight away we just don't have enough participants, okay? And it's not powerful enough.
We repeated the study, or we got another study with the same confidence interval, like this situation. Would that mean that our sample is not diverse, or something else?
Well, if you've got the same result, that's good. That's kind of replication, isn't it?
Yes, but in a larger sample.
In a larger sample?
Yes.
Okay, with a larger sample, the confidence interval would be smaller, okay? If the mean was in the same place, and if you shrunk this confidence interval, let's say the mean was in the same place, you would end up with it being like scenario A in that slide just a couple of slides back, where we had it being statistically significant, so it didn't cross 100 here, and it didn't cross 110 either. So it would be statistically significant, but not of practical importance. Okay. Okay. So yeah, you would say do another study. There are problems with this. Let's say these people really want to find, they're really keen, they're funded by omega-3 fatty acid, big company, and they say, you know, do a study. They do a study and they get this result. Say, look, do another one, you know. So they fund them for more studies. Still comes out not significant, not significant. And they say, well, just, you know, keep going. And eventually they will get a statistically significant result, okay? You will always get a statistically significant result, even if fatty acids don't do anything. So this is a bit of a problem in statistics, okay? It's nice to replicate. It's better if another group, independent of the first group, replicates. If they get the same result, fine. You can be more confident. It's nice if it's kind of like a large enough sample size so that the confidence interval is small, and so that you can say that, yeah, there may be a statistically significant effect, but it's actually of no practical importance. Like scenario A above, this one here. This is what we could get, this result, A. Okay. Okay.
There might be
Yeah.
a question about the graph for this.
Right.
Yeah, they're asking what is Z equal to 1 in this graph, but equal to 2 in the previous one.
It's not 6 in the previous one. Z is 2 for, sorry, Z is 1 for C and D. Okay, and for A and B, it is 6. Okay, so if you read these slides here, A and B outcomes and C and D outcomes, that will explain it. I have explained it already. Please read this again. If you still don't understand it, then ask me again if you want.
Someone is asking if you could summarize ABC and the keys about it.
The what?
The key points.
Key points. Okay, let's do that. A, statistically significant, but not of practical importance. B is the opposite, even though the Z is actually the same. Okay, so this is statistically significant, but it's of practical importance, clearly. Okay. Okay, they're both statistically significant, but B is of practical importance. C, is not significant, but conclusive because the confidence interval doesn't include 110. And D is inconclusive, okay? So in fact, A, B, and C are all conclusive results, okay? We can write these up, report them. They're useful to people reading about these studies. But D, we can't actually get much out of this. It's looking promising. It looks like the vitamins are doing something, but there's just too much variability. Okay. Now, I mentioned that the usual way is to increase the sample size, but maybe there's other things going on. Maybe you are, there's a lot of variability in your data. Maybe the children are from many different backgrounds and their age range is very big or something, okay? This will add variability to the data. So what you want to do, you want to select a more homogeneous group of participants, children in this case, to do your study. Okay, any other questions? Okay, so if the 95% confidence interval includes an interesting effect size and excludes the null hypothesis value, but also contains uninteresting small values, then that might suggest that more data should be collected, even though there is a statistically significant result. So this is the sort of thing. And this is actually pretty typical of a lot of studies that are published, okay? They say, well, yeah, our mean is pretty good. It's near 110 and it's statistically significant. People generally just look at the p-value and say, oh, it's less than 0.05. Ah, this is important because it's statistically significant. Not necessarily so. It could be that the mean is up here, near going up to 120. It's possible, okay? But it could also be right down here, near to 100, okay? We don't actually know. So we should repeat the study with a larger sample, okay? So that we can be more confident about the result. Okay, I think that's the last slide. So any other questions? Okay, do you understand confidence intervals? There's no one saying yes. Okay, after 2 hours, all right. All right. Do you understand p-values? So, all right. Do you understand effect size? Okay, what about sampling error or sampling distribution and standard error? Okay, these are all key concepts for statistics. If you understand these 4 or so concepts, then that's you. You really can do statistics, all right? I agree they're slippery. P-value especially is very slippery. And I've shown you that the p-value is not everything, okay? Just looking at a p-value is not gonna be much use. You need to look at the effect size. And the other thing about the p-value I mentioned with replication, if you repeat a study enough times, even if the null hypothesis is true, you will always get a statistically significant result. If you repeat the same study with null data, okay, there's no effect there, the treatment doesn't do anything, 100 times, because we're using a significance level of 5%, approximately 5 of those studies will report results that are significant at the 5% level, okay? They will give you p-values less or equal to 0.05. One of those studies will probably have a p-value of 0.01 or less, okay? Because it's 1%. All right, so we will have a break now, all right, till 4 o'clock, and then we'll do the lab. Okay, great. I'll resume recording, okay. All right, so let's start this practical. For those who are using Zoom, I've just uploaded this